We can now check our results to ensure that our simulation makes sense. While we do not have experimental data to validate that we solved the correct mathematical model, we can verify our results by investigating whether we solved the selected mathematical model correctly. Firstly, we can work to verify our results by performing some sanity checks and ensuring that our boundary conditions are satisfied. Looking at the velocity contours on the inlet face, we see that it is nearly constant at the prescribed value of 5 micrometers per second. Similarly, looking at the outlet face, we can see that the pressure is constant at a gauge value of 0 pascals, which matches the applied boundary condition. We can also investigate the boundary conditions on the walls. In this screenshot, we can see that the velocity is very low near the inner and outer walls of the model from boundary layer development. The same can be seen around the obstruction, with this view showing the extension of this slightly behind the pillar. This is consistent with the applied no slip and no penetration boundary conditions applied at the walls, leading the velocity magnitude to be 0. This shows that all boundary conditions were satisfied as expected. Next, we can work to determine and reduce the numerical errors in our solution process. To start, we can look at the mass flow rate report. Here, as shown before, we can see the mass flow rate through the inlet and outlet boundaries. At the bottom, the net results value shows the difference between the calculated mass flow rate entering the bone structure and the mass flow rate leaving it. We can see that this value is extremely small. This is a good indication that our solution has converged and that the overall errors are small. We can then work to reduce the numerical errors in our solution process in 2 ways. Firstly, we can run the solver for more iterations to decrease the residual values further. Here's a plot of the residuals after the solution process. Running the solver for more iterations will update the guess values more times and drop these values even lower. This reduces the linearization error and will help the results to converge to a more accurate solution. Secondly, the mesh can be refined to contain more elements. This means the solver will find values of the primary unknowns at more points in the flow domain, and the discretization error will be reduced. This can be easily achieved by reducing the element sizes in the meshing step. Since our convergence criteria was already extremely small, this is likely to have a larger effect in reducing errors. We can expect the largest changes to be seen on the wall shear plot, since it is highly sensitive to the mesh near the boundaries. Here's an example of a sample refined mesh. This was created by reducing the sizing on all faces to the value shown here. This leads to over double the number of elements and serves as a basis for more careful refinement. I encourage you to go through these steps by yourself to verify and improve the solution results.